I am here to introduce our own Catharine Winstanley, who really needs no introduction. She,
better or worse?
I don't usually do the formal reading of the CV, so for these talks, so I won't do it here. But Kath, you know, has been a professor in the Center for Brain Health in the Department of Psychology, doing all this amazing groundbreaking work on motivated behaviors in rodents and people, and their influence on cognition. To be super vaguely general.
I'll take it. It's good. It's good. Okay, so thanks, Beck. I'm just going to turn off, get rid of the video from my screen. Not least because I just hate seeing myself. Let's see if I can just go away. Okay, I don't think I can actually close that. Just, I don't know. We'll just stick it down there. I think that's best I can do. Does anyone know how to get rid of the PowerPoint thing, or is that okay in the room? We'll just deal with it. It's a miracle that it's even this good. So first of all, I'm going to apologize to the students whose work I might actually butcher while I attempt to present it. This is, for those of you who are familiar with A, my crazy life, and B, who've ever been on a symposium with me, the idea of me skating in about 2 minutes after my talk was supposed to start is not actually that unusual. But in this case, it's because I was desperately trying to put in all the amazing new data that my trainees have collected pretty recently, having given them not really very much notice to get it to me. So it is not their fault, it is entirely mine. So my motivation for giving this talk today really is in response to some of the excellent clinical talks that we had in the previous round series. And I think it's just really encouraging and inspiring, makes me feel very optimistic that we had so many clinical scientists who were willing to give their time and their trainees time to come and talk to us in this integrated research pillar series, because that's really what we need at CBH to try and get the clinical groups and the foundational or preclinical groups talking to each other. So, you know, thank you from the bottom of my little translationally motivated heart to have so much buy-in across the board. So I wanted to give a talk that tried to sort of speak to or link to some of the research that we've already seen. But that's actually trying to give a talk on 3 different, somewhat related, but not really, lines of research that we've been doing. The first looking at the effects of chronic ropinirole, and this will speak quite directly to Andrew Howard's work that he presented a few weeks ago. Oh, actually, Beck, that reminds me, can you record this?
Thank you, I am.
Okay, cool, so it's on, okay. Not because it's going to be amazing, but just in case I can say, oh, refer back to this. Well, we've been looking at trying to model iatrogenic gambling disorder by giving animals chronic ropinirole. So ropinirole is a dopamine D2/3 agonist that is one of the compounds that causes impulse control problems in patients with Parkinson's disease and other movement conditions who are prescribed this medication. I then, rather optimistically, I'm also wanting to talk about some of the research we've done looking at the effects of chronic administration of cannabis products. And this is work that Melanie Lysenko-Martin has really championed, and she's here in the audience, can answer all the technical questions. And one of the motivating forces here was that we wanted to try and give cannabis products in a way that better represents how human subjects actually take it. We've worked with acute injections of THC before, but unless anyone wants to correct me, as far as I'm aware, no one is going around injecting pure THC into their abdomen, and certainly not into their veins. Experts in this field, people like Matt Hill and Ron McLaughlin, who was here recently, will tell you that how you administer THC really matters. So a really high dose all at once is highly aversive to almost everyone who takes it, unless you have been consuming cannabis since you were quite young and have done so regularly every day for like 30 years, and your tolerance is really high. That's not these rats, and it's not most of us. So if we're actually trying to model how humans enjoy or may develop a problem with THC, then just stabbing rats with acute injections of pure THC probably isn't going to get that. And then finally, very hot off the press, is research that we tried to start in June 2020 and has literally been almost 2 years in the making, which is do we see any effects of psychedelic medication? Particularly, we're going to look at psilocybin in our rat gambling task. And I'm going to explain why we think that's useful. And Dimitri and Chloe and Shrishti, who are involved in doing that research, are also right here. So I haven't got very much time to do all that. So forgive me if I gloss over the introduction, because, you know, I figure that if you've been coming to rounds, you know why some of these things are important. However, one thing I'm not going to gloss over is that I have to acknowledge that we are standing on the ancestral and stolen territory of the Musqueam people. All the research was conducted here, and we just need to be mindful and acknowledge that we are beholden to them. And I acknowledge and I'm grateful for their stewardship of this land for thousands of years. And I'm working to do all I can to make my lab and UBC more culturally safe, and to try and decolonize the work that we do. I also need to acknowledge the fact that all this work was done by some amazing students and trainees, some of whom are pictured here. I'm very fortunate to work with them, so thank you very much. We also collaborate with Luke Clark, who I know can't be here today, Maria Chakasaba, on a lot of the human subject stuff, and Lester Tong. I don't have time to talk about that, but we do have about 10% of our research now is in human subjects, and we are increasingly trying to be translational in what we do. Okay, so the outline of the talk. I've just tried to teach undergrads how to give talks, which is hilarious, because one thing I wouldn't say is like, put in your slides 2 minutes before you're supposed to give the talk. But a good outline slide always helps to give you some idea of where we're going, and you know, make the first thing you say the last thing they forget. So while I still have some of your attention, what I'm hopefully going to show you is that chronic ropinirole, this D23 agonist, which we're going to give in a slow release formulation to try and model the way it's administered to human subjects, can increase cue-driven risky choice in particular. It also increases motor impulsivity, which isn't something I'm going to talk about very much, but which happens regardless of the presence of cues. And what I really want to talk about is this interaction with circadian rhythms, because the importance of this really came through in Andrew Howard's talk, that most subjects who are experiencing problems with this medication in terms of impulse control or gambling addiction, there is a diurnal rhythm to it, and it gets a lot worse at night. So just bear that in mind. And then hopefully going to talk about chronic oral cannabis work, which is the stuff that Melanie's done. We bought our products from the BC government online and just ordered it. So this is the same stuff that you could theoretically use at home if you wanted to. We've got a sativa brand and an indica sort of cultivar dominant strain. And the two have different effects. So that's kind of interesting, and not something you'd necessarily expect in terms of decision making, but both of them increased motor impulsivity. And again, for those of you who have been following the cannabis literature, this is kind of novel, because typically you just see sedation when you give these products. But in human subjects, there are reports, rather, so I can use grammar correctly, of disinhibition, particularly with chronic use. This can lead to impulse control issues, and we've managed to capture some of that. And in particular, it looks as if we're getting an increase in a form of impulsivity called negative urgency. And the importance of that, again, I will hopefully get to. And then finally, we are going to talk about the effects of acute systemic psilocybin, particularly at incredibly low, and these were doses deliberately designed to be microdoses. This is a very contentious approach in the literature, with a lot of people saying that they don't see any effects, that microdosing is all placebo and you only see it if you believe it's there. We have reason to suspect that this task that I'm going to be talking about is going to be very sensitive to these drugs. But what we didn't expect was that females would be more affected than males, and that is really clearly shown by the data. And I'm going to get into the matching with a 5-HT2C antagonist and how this might be something that's really important to consider in your preclinical models. Okay, what is the task? At least we're going to use the same task. So we're going to be using this version of the rat gambling task with lots of reward paired cues in it. So for a change, I'm not going to use my 16-year-old animations, because even I'm starting to find them kind of cringeworthy. But this is a schematic of how the task works. So we have an array of 5 holes at the back of an operant chamber, and we can illuminate these holes using computer code, right? So the task starts. There is then a 5-second intertrial interval during which the animal has to withhold from making any response at this array. So everything's in darkness. If the rat just can't withhold, because these are trained rats, they're going to learn every day that this is what they have to do, that lights are going to come on, they can earn some reward, and they get kind of amped up, right? So sometimes they just go early. That is our premature response, and that is our index of motor impulsivity. We ripped this right out of the 5-choice serial reaction time task that Trevor Robbins' group has developed, in use since the 80s. And it has a lot of translational validity. We know a lot about its biological basis. That's what we're using. That's our impulse control measure. Now, then we get into the decision-making phase. So this is different from the impulse control. So the animal gets to choose from these 4 options, each of which is associated with a different number of sugar pellets, shown here from 1 through to 4. And also a different probability of reward delivery and consequently of timeouts. So they either win reward or they're punished by a time during which they can't earn any more sugar pellets. Now, the timeouts are shorter and the rewards more frequent for the smaller reward options, right? So generally speaking, if you're feeling safe and you want to maximize your sugar pellet gains, you should be choosing more from these options that are associated with smaller per trial gains, that are delivered more frequently and are associated with shorter punishments. So the animals have 30 minutes to maximize their sugar pellet profits on this task. So they have to learn which of these options gives them the best bang for their buck. So the options associated with 3 and 4 pellets, which we'll be referring to these as P3, P4, while they are associated with larger per trial gains, these rewards are delivered less frequently, the timeout periods are delivered more frequently, and are longer. So what happens is the animal ends up sitting in timeout period for longer. That eats into the time they have available to earn reward. So if we calculate sort of like a maximum possible pellets available, assuming the animals stay on task constantly and are like little robots, which we know they don't do, they groom and they look around, but assuming a constant sort of faffing about length of time, then the maximum amount of reward they can earn is on P1 and P2, and P4 and P3 result in significantly fewer pellets over time. So these are going to be the risky options, these larger per trial gains, but more frequent and larger losses. Very similar to the Iowa gambling task. Okay, so I mentioned that we're using version with the cues present. And we did this because we really want to try and sort of maximize the similarity between this gambling-like paradigm and commercial gambling products. Whereas if you've ever gone to Luke Clark's casino lab over in the O'Dane Center, as soon as you start playing with the slot machines, there is just tons of sound and light stimulation that are present. And we realized, my then graduate student, Michael Barris, and I, that we had none of that sensory stimulation in the task. We're like, oh, I wonder what would happen if we just put in some flashing lights. It was supposed to be a master's project before he went on to do some real science, and has since sort of become this all-consuming obsession of mine. So this is what the cues look like from the rat's perspective. Hopefully the sound and lights are all going to work. So we've paired the most interesting cue, the one that is most complex and most variable, with the largest reward in this version. Just like if you win big on a slot machine, it lights up more vigorously than if you win small. But each reward is associated with a cue. If you want to know more about cue outcome associations, I can give a separate talk on that and what's important and how and why. But that's not what we're talking about today. Okay, so rat's eye view. Okay, that goes beep. Damn it. And this goes beep, 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 beep. Okay, I can never get the sound to work in, in the clutch of a talk. Okay, so that's a P1 versus a P4 win. All the other rules of the game are exactly the same. The chances of winning, the chances of losing, the size of the wins, the size of the losses for P1 through P4 are identical. Only thing we've done is flash some lights and play a little tune when the animals win. And we get a huge increase in risky decision-making that we have now reproduced about 20 times, and other labs have also seen. So this is what data from the IGT can look like. So we can graph the individual options, P1, P2, P3, P4, and their percent choice. Here you can see the cued group are choosing P2 less and P3 more. This is from our original paper in Journal of Neuroscience a few years ago. We can also calculate a score, and we do this just based on the Iowa gambling task data, where you take the number of advantageous choices and you subtract from that the number of disadvantageous choices. So you take your P1 and P2 and you subtract your P3 plus P4. If that score is positive, the animal is making good decisions on average, and we call these animals optimal decision makers. If it is negative, they are risk preferring, and they are making more risky choices than optimal ones. So in the uncued task, this is sort of 32 rats, pretty representative. Generally speaking, nearly all the animals are optimal. So you have to look quite hard to get risky animals, and sometimes per cohort of 24, you may only get 1 or 2. Here we have about 5, not a huge number to work with, but you do get them in the uncued task. Despite equivalent amounts of training, etc., some animals just go risky. In the cued task, however, you go from like a risky rate of 10 to 15% to a risky rate of about 50. So now we have far more animals that are here in this risky quadrant. So, cues are bad. Moving into story 1, let's look at the effect of ropinirole on this decision-making behavior. So this is work that was done by Mowafaghian when she was an honors student with us. She's now, goodness, probably about 2 years away from finishing her PhD at Stanford. And this was how we did the experiment. We used slow release mini pumps. So this is an osmotic mini pump. So we load in all the drug for 28 days. We used 2 different doses of drug, 2.5 and 5 mg per kg. We've actually done the same kind of experiment using different behaviors multiple times. Now, happy to talk about that again offline or in the pub or what have you. Then we just start the training. So this is, we do some forced choice training, which we do in all our tasks, where only one of those 4 lights illuminates, and the animal has to respond there for the computer program to move on. And we do this to make sure that the animal has an idea of what the contingencies are associated with each hole. Because we don't want animals to say, poke a couple of times for P4, get a 40-second timeout penalty, and therefore never touch it again. Not because they're risk averse, but because they figure all that happens when you respond in that hole is you get this whacking great timeout. So they're not avoiding it because they don't like risk, they're avoiding it because they think it doesn't give reward. And that's not cognitively what we're interested in. So they have 7 sessions of forced choice training in this task, and then they have free choice training. This is where they're just allowed to choose freely. Because we can only load enough drug for 28 days and the schedule that we were working with at the time and Layli's availability, we got 14 free choice training sessions out, including in addition to the 7 forced choice. And then we also have some testing and washout that I'm not going to have time to talk about very much. These are the data. They were published at the beginning of this year in the Journal of Neuroscience. So the lighter pink color is the lower dose of ropinirole. That's 2.5 mg per kg per day, released over a 24-hour period. And in purple is the highest dose. And what hopefully, let's not look at that. What hopefully leaps out at you is that doesn't look like there's much happening in this graph, and yet these 2 pinky lines are just tanking in this. So this darker phase here, this is where the drug is on board. So when the animals are learning this task for the first time, they've got drug on board. If there is a slow release D23 agonist mini pump implanted, they make far riskier choices, but only when those wind-paired cues are present. So there's something synergistic about adding in these wind-paired cues to make the test more similar to an electronic gambling game and having that agonist on board. So it's not just the drug, if you like, it's the drug plus exposure to this as realistic as we can get, or it's not even that realistic, but incorporating some of the structural characteristics of a gambling task, this kind of rat simulation of that seems to be really increasing risky decision making. I will say that on both the uncued and the cued RGT, we saw an increase in impulsive responses. So that motor impulsivity seems independent of the task. That just seems to be something that ropinirole does just by itself. Okay, we were really interested in trying to figure out why this was happening. And we did some CFOS immunohistochemistry, or what is referred to in fancy with CFOS imaging. So the animals were euthanized 90 minutes after they completed the task, so that we could look at CFOS expression in different brain regions to try and see if we could tell what was different between animals that were treated with saline versus ropinirole on the cued and uncued paradigm. There's quite a lot of data here, and I'm just going to sort of point out the highlights, if you like. So this is just showing that we can actually see CFOS. One thing that again might sort of leap out at you is that in the uncued ropinirole quadrant here, we actually look like we're getting the most sort of dots lighting up. And yet that was the place we saw the least behavioral effect. You are not going mad. That is actually what we found. So if I can sort of draw your attention to a couple of things, over here where we're looking at midbrain dopamine neurons, so we did co-stain with tyrosine hydroxylase, the cue task, these neurons are not as active as you might think. So we've been working with this, we first looked at these data, we're like, oh, we've got cues, we've got risk, we've got reward, this is going to be a hyperdopaminergic state that's driving risky choice. Every single experiment we've done to try and prove that, we have found exactly the opposite, that there is something about the presence of the cues on task that is dampening basal dopamine release. Perhaps because there is such great evoked dopamine release, I don't know. But in terms of tonic activation levels, it looks like it goes down. And then when we add ropinirole on top of that, there's not much of a further decrease. But you can really see this in the uncued task where we add ropinirole, we get a decrease in midbrain dopamine activity. And that may not be surprising given that we're looking at a D2 agonist, and D2 receptors are inhibitory when they're in their autoreceptor location. Right? So these are located on the terminals, or on the soma of midbrain dopamine neurons, and they do form a negative feedback loop to shut off dopamine release. And over here, you can see there is some sort of upregulation of prefrontal activity, and we found exactly the same sort of pattern across every frontal region that we looked at, again, only in the uncued task. So perhaps this is a compensation for the fact that there's this ropinirole on board, because they're still making good decisions, even though ropinirole is there. Laley also did some sort of network analysis of all these data to try and look at where, within individual animals, where the activity was correlated. And we can see in the uncued task, the pattern looks very different from the cued. So these red lines indicate that activity is correlated, and that there is the thickness of the red line indicates the strength of the correlation. And in blue, all that indicates, it doesn't indicate a negative correlation, it indicates there is an anti-correlation. So activity in sort of the SNC and VTA is not affecting activity in the prefrontal cortex, or not driving patterns of correlated activity. I shouldn't say, I can't speak to whether or not they are influencing each other.
Kath, can I just ask a clarification question, just because I'm used to looking at bold responses? What is the measure of activity and how it's correlated here?
CFOS.
So CFOS. Okay, it is CFOS.
Yeah. Okay. So it's not super. It is what we do in the absence of neuroimaging in rats. Yeah, it's all ex vivo. But the pattern looks very different in the cued task, where it looks like we've got really strong synergy between at least one dopaminergic nucleus, the accumbens, and the orbitofrontal cortex. So that's sort of interesting. This orbitofrontal cortex piece, hold that in mind, because that comes up later. When we look at the effects of ropinirole, however, this was really surprising to us, because I would have thought in the cued task, we'd start to see, I don't know, like lots more dopaminergic input, driving everything. We'd see an increase in correlation. Maybe the frontal cortices would be less online. All of the interactions with the frontal cortex or the striatum just go away in our network analysis. In the uncued task, it looks like we see some kind of correlation emerging that wasn't there before. But in the cued task, it looks like the SNC and VTA are in sync and everything else is just off on its own somewhere. Again, this was really unexpected. It made us wonder, maybe we've lost some sort of really important learning signal that was arising from these dopaminergic nuclei. The reason we might suspect this to be the case is that when Laley then went back and looked at how risky the animals were at the end of training, and compared that literally on the sort of the last session, the session before we whacked them, and then looked at the degree or the ratio of activity of those midbrain dopamine neurons to prefrontal cortex, that ratio was the only thing that would predict how bad the animals were doing. So the more risky they were, the lower the midbrain to PFC dopamine ratio. So for those of you who are familiar with Kumar Narayanan's work, he's actually shown that there is a loss of VTA to prefrontal, I think it's gamma oscillatory activity, that is driving cognitive deficits in Parkinson's disease. So this actually potentially does have some correlates clinically, but he hasn't looked at whether or what happens in individuals that are treated with ropinirole and then develop impulse control problems. So that's rather cool. But the question we then had was how is, and we've had for a long time, like how is it that ropinirole is causing these things? So we know that ropinirole is a D2/3 agonist. So is it the D2 bit or the D3 bit that's causing these problems? Now there's this very dominant hypothesis in the literature that it's the D3 receptor because there aren't many D3 receptors outside of the limbic neural circuitry. So they're particularly strongly expressed in the nucleus accumbens, which is a region that we know is associated with reward-related learning, and that mesolimbic projection from the VTA to the nucleus accumbens is central to the actions of many addictive drugs. So it seems like an obvious hypothesis that when you give this medication to some individuals with Parkinson's disease, you drive that projection harder than it would otherwise be driven, and you get impulse control problems. So I know, because mighty Stan Foresco is in the audience, that he collected some data quite a few years ago now that didn't seem to support that view, in that when he gave a D3 agonist acutely to animals performing a probability discounting task, he got the opposite pattern of effects. He didn't get risk seeking, he actually got risk aversion. So Brittany Russell, as part of her PhD, along with a talented group of undergrads, tried to look basically and just compare these effects. This was done in a pretty large group of male Long Evans rats. We have low dose of somanerol, which is a D2 agonist. We have a higher dose of the same compound. We have a low dose of a D3 agonist, PD128907, and a higher dose. And we compared them in this study to safety. So because we're not going to use mini pumps at this time, because these drugs aren't always very soluble, and mini pumps are damn expensive, we just thought we'd go with bolus injections. They occur daily 10 minutes prior to testing. So again, I apologize for the color scheme. I didn't tell Brittany that I needed these graphs until very much at the last minute. So there is this sort of like shading from light green through to dark green, but it hasn't really come out on my computer. So over here are our control data. So what we're looking at here is from week 1 through to week 6 of administration. And generally, this is very similar to the pattern of behavior we see in this task, is that animals start out, this is our score, so the more optimal, the higher the score, the more optimal the decision making, the lower the score, the riskier. Animals start out okay, and they get riskier and riskier and riskier and riskier. That's basically what happens in the task. That's what we see in control animals. However, it is not what we see when we give either dose of the D3 agonist. It's not what we see when we give a high dose of D2 agonist. If anything, they're getting better. We see some increase in, or relative increase in risky choice in animals given the low dose of somanerol, but nothing that looked worse than control. This was really surprising to us. We thought, one of these two would do it, but we didn't get anything that looked like ropinirole. Okay, what happens if we give them both together? Maybe there's something about having both agonists on board at the same time. Something that I'm trying not to think about is the fact that D2 and D3 receptors can form heterodimers, and those heterodimers can have different effects on striatal interneurons. So there may be something about just the structure of ropinirole that means, or pramipexole, that means it binds preferentially to those heterodimers. We don't have heterodimer selective drugs available to us right now, but we thought we'd see what would happen when we just gave D2 and D3 agonists. Okay, same kind of idea. We combined the two lowest doses of PD and somanerol. We also just did a few extra low dose PD, low dose somanerol, and we had some saline controls. But in response to a question from our committee member, Dr. Foresco, he said, why don't you just run the ropinirole alongside this group just as a positive control? Now, this was a really good idea because I've actually omitted a couple of key experiments from this whole narrative. The first was that a master's student, Hannah Brody, tried running this in females, the ropinirole study. Just 16 and 16 females, some with ropinirole and some without, and we didn't see any effects of ropinirole. And we were like super excited about this, and so excited we wrote a Kickstarter grant on it, being like, oh my God, there's like this massive like dissociation across the sexes. I got very excited about getting a CHR grant looking at, from gender health and all that committee that isn't BSA. And we were going to look at the metabolomics following ropinirole administration as to why we're not getting effect from females. We weren't that worried at this point. Then we actually tried to run that metabolomic study, and Graham, I'm not sure if he's on the call, it was a really tough study to run with 64 animals, and he was running it as well as he could, given all the other things he was trying to do. And we didn't get an effect of ropinirole in our males either. And Graham, bless his heart, was like, it's probably something I've done. Like I was draining the sarcomas really extensively. Maybe I pulled too much of the drug out. I was like, well, we'll take these animals as positive controls, and at least we'll learn how to do all the sac. All that tissue is still banked. So now I'm bring you up to present day. So Brittany's done these ropinirole studies many, many times before on different tasks. And so, okay, let's do this. Here are the results. Okay, so on the plus side, we're sort of getting some risky behavior in animals that are treated with the low dose of somanerol. Again, we're not getting anything with a combination of D2 and D3 agonist. Anything they're getting better. Like, so here are our controls. These animals are not vulnerable to the risk promoting effects of the cues. However, some of you may be like, where's your effective ropinirole gone? These animals, your animals treated with ropinirole, and they don't look particularly risky. They don't look any different from your controls. Panic was starting to set in my mind. Like, have we just published something that is a lie? Because I can't reproduce the effect now. We've just done 3 failed replicates. And so we're talking in lab meeting about what was different, because I don't think, you know, Lady's an amazing student. I don't think she made this data up. I've looked at the data, looked really solid. We've analyzed it up the wazoo. So why aren't we replicating her effect? And one thing, it turns out, is that these animals were run in the morning. All the other animals were being run in the evening. And we're on reverse light, which means that all our animals are being run in the dark, but some of them are being run closer to the time when that light dark switch turns on. Others are being run later. And I still remember Chloe, you said, I was okay, we're going to try and run this in the morning. And you being like, really? You really think that's going to have an effect? Like, whew, you're grasping at straws, lady. And I kind of thought I was. But we did it anyway, because there is actually a story about the time of day mattering for the effects of these medications. And one of the sort of big things, of course, that happens when the lights go off is that you get an increase in melatonin. And melatonin can suppress the release of dopamine from terminals by altering calcium influx into the cell. So melatonin is actually going to dampen the endogenous dopaminergic signal. There's been a whole article, conveniently, that I found written about why it is that this time people with restless leg syndrome have worse symptoms at night. If you can just focus in here, there's a lot of different things it could be, but one is that as melatonin rises, this leads to a relatively hyperdopaminergic state. Now, obviously, we don't know whether that's happening in our animals. I'm hoping that we're going to do a study to try and prove whether this is what is happening. But the first thing is to see, okay, if we run the same experiment as we've been running previously and we test the animals in the morning, do we get the same effect of ropinirole? Yes! Yes! So it matters. It really, really matters when we're running these tasks. And we're now seeing it in both males and in females. So we didn't have a sex-specific effect. We had a time of day specific effect. We've never seen any of our pharmacology show this kind of real sensitivity to light cycle, or rather to time in the day. And it could be because we're using very slow release drugs. So we're not using a big bolus. We're using, you know, the concentration of ropinirole that is going to be in the bloodstream at any particular time is incredibly low, because this is 5 mg per kg over the course of a day. So what we're hoping to do now is to look into that. But when Andrew Howard said just the other week or month that yes, symptoms are really, really noticeably bad in the evening, you know, as you're getting that transition to nighttime, I was like, this could all add up, perhaps. Okay, so this is very much all stuff that's a work in progress. So again, hopefully there will be buy-in from you all. That's where we are with that, and let's move on to part 2, because I'm running out of time, which is cannabis, which is the work that Melanie has been doing. So I've talked to you a bit about risky decision-making that we see on the task. One of the things that Melanie and also Craig were interested in looking at was whether there's a relationship between risky decisions, and motor impulsivity. Because we see clinically, we clinicians see, in disorders like substance use disorder, that generally high levels of motor impulsivity, high levels of risky decision-making, high levels of other forms of impulsivity, they all sort of go together once you reach a clinically significant level. But in a general population, they don't necessarily track each other. You can be high in one form of impulsivity, not in another. You can make lots of risky decisions, but not necessarily make lots of motor impulsive responses. So we also know that the outcome of these choices, you can either get a reward that's safe, you can get a reward that's risky, or you can get a punishment. And a kind of impulsivity that researchers have become very interested in of late is this idea of negative urgency. So negative urgency is when people act rashly or impulsively when they're in a negative mood state. So when something bad happens. This can be contrasted with positive urgency, which is much more what me and my family exhibit, which is doing impulsive things when you're feeling good. Like you just get a grant funded, yeah, let's go out, do something fun. Life is good, I'm gonna buy myself something nice as a treat, rather than life is bad and I need to cheer myself. Negative urgency is the kind of impulsivity that is particularly associated with opiate use. So high levels of negative urgency in at-risk youth are associated with a greater likelihood of transitioning to opiate problems. So literally almost exactly the same time as Trevor Robinson's group started to do this, we wanted to see if we could pick up anything that looked like positive or negative urgency by looking at when animals made premature responses on the rat gambling test. So did they do it after big wins, after little wins, after losses, and did it matter what the size of that loss was? So Mel and our statistics consultant, Craig Hutton, started looking at data from 280 rats, just once behavior was stabilizing. So this is after they've already learned, or most of the learning has been done about the reinforcement contingencies. So like the last 5 sessions, if you like, and looked at the data from 120,000 choices, big data set, try and figure out if there are any patterns there. So what comes out statistically, but maybe not sure if it's functionally significant, is that in general, rats are actually less likely to make a premature response after a loss. So if this error bar doesn't touch this dotted line, it means that there is a significant difference from chance. So interestingly, at ACMP year before last, Trevor Robbins presented exactly the same finding from the 5-choice task, showing that animals are less likely to make a premature response after a punishment. So they are slightly more likely to make a premature response after a win. Interestingly, we see a bit of a difference depending on whether animals make more good decisions than bad decisions, i.e. whether they are optimal or risk preferring. But this is only in the uncued task. So our optimal animals are sort of even less likely to show negative urgency than our sort of majority. This differential sort of goes away in the cued task. So these animals that are risk preferring in the absence of cues, what might be regulating their premature responding could be a little different from what's regulating premature responding on the cued task. Again, that's a totally separate talk. I just wanted to, yeah. So generally, we don't see very much negative urgency. It's kind of the take. And the better the animals do, the lower the level of urgency. This is the experiment that Mel ran with the cannabis products. So this is cannabis oil that's already heat treated and ready to go. So you can put it under your tongue if you wanted to. We mixed it with Boost, which is sort of a very sugary, syrupy, glurpy drink that is used mainly in seniors who are trying to boost their calorie intake because it's so calorific. And we chose something so like milkshakey in Boost because we wanted to mask the taste of the cannabis because it does smell and theoretically taste quite strong. And the animals don't like the taste of it. So we mixed it with this sort of rather gross strawberry milkshake, and then they drank it from a syringe. We started dosing after they'd already done sort of the pre-training bit, which is just, can you poke your nose into a hole when it's illuminated? We do get some measures of impulsivity from this because it looks just like the 5-choice. So the trial structure is the same as the RGT, only one light is on at a time, and they always get reinforced if they correctly put their nose in that hole. So it's like a really simple visual attentional task, visuospatial attentional task. We have 10 animals that are taking the sativa version and 10 animals that are taking the indica version. And yes, we are aware of the controversy about whether there really is any difference between sativa and indica, but you can't argue with data. So animals treated with the cannabis sativa cultivar took longer to figure out that this was the best option. So what I'm graphing here is the percent choice of P1, P2, P3, and P4. So these are risky choices. These are the more optimal choices, and P2 is the most optimal choice. So the sativa treated rats took longer to figure out what the right answer was. All the animals treated with cannabis were more impulsive than controls. There's sativa, there's indica, there's our control group. Even in this smaller group, so we had 12 controls, we see the same sort of slight decrease in negative urgency. So in general, animals are less likely to be impulsive after a loss than a gain. That isn't as present in the animals treated with cannabis. And once they've acquired the task, animals treated with indica are actually more likely to show negative urgency. So they are now making more premature responses after a loss than a win, which is not the kind of impulsivity that we'd like to see. I don't have time to say any more about that, but I will say that Mel, through a Herculean effort, in collaboration with Brian Christie's lab, has managed to get adolescent female rats to vape THC. And hopefully this video is going to work. So what you're seeing is little baby, or not, they're adolescents, so they're PND 40-ish, vaping THC. So that is THC vapor. It is not a cannabis product. It is pure THC that is then, it's not pure, as in it's a concentration that is delivered, that is designed to mimic the kind of effect you might get from smoking a doobie. And you can see that the animals are doing it. And the first time I saw this, I was just blown away. So there they are, sniffing away at the vape. This is actual data to actually show you that it works. So these are the number of times in animals in the control group would vape the vehicle, which is PEG, versus PEG plus THC. And it's hugely significant. So yes, they are self-administering it. And this is what the individual differences look like. So yeah, you can see that there are some animals that don't really like taking it versus some animals that do. We are so soon, hopefully any day now, going to get the brain THC levels back from Robert Laprairie. But I think he's run 2 animals from the top, middle, and bottom groups in terms of the concentration of THC in the brain. And the homogeneity in terms of the concentrations is remarkable. So when we do the same thing with oral THC, we get a lot of variation in terms of how much THC there is in the brain and in the plasma. This is much more tightly controlled. So we would love to actually move to doing this kind of self-administration or this kind of administration of cannabis, because again, it more realistically ties into the way human subjects are using it. And hopefully we can then combine it with the gambling task, because I'd love to see if we get this kind of deficit and impulsivity. Okay, part 3. I'm gonna get there, I've got 2 minutes. There'll be no questions. You have to come to the pub if you want to ask a question. Part 3, psilocybin. Again, there's been a number of conversations and discussions about how important it is for us to be able to do this research in the clinic in terms of trying to figure out what psilocybin does. There's a lot of press around how it looks like it could be a novel and effective treatment for major depressive disorder. It's really encouraging clinical trials. And if it works for major depressive disorder, it might work for other things. And what might it work for? There is a lot of hype in this space. There are a lot of people trying to make money, which makes it very difficult for anyone who actually wants to do some research with this compound. We are not out to patent bust. I'm not going to tell you that, you know, we've got some special proprietary molecule found only in a mushroom grown on the Himalayan slopes. Or, no, we just want to see if psilocybin works. That is all we are trying to do. 2 years to give it to rats. 2 years. Okay, sorry, I'm a bit bitter. One of the things to note, and this came from a review by Carhart Harris and Guy Goodwin, who are sort of the two psychiatrists probably most active in this area, is that, you know, even though sort of conventional antidepressants also work on the serotonin system, by conventional I mean Prozac or venlafaxine, you know, these are SSRIs or SNRIs, but they work very differently. So these will target sort of global serotonin levels. They are serotonin reuptake inhibitors. They're just trying to, if anything, potentiate serotonin signaling, or perhaps just keep it within bounds, right? So you are just almost like washing out any phasic signal with some of these drugs. What we think is happening is that we're getting more postsynaptic 5-HT1A receptor signaling. Your limbic system is less responsive, you're less anxious, less sensitive to the moment-by-moment triggers that could spur anxiety or stress or impulsivity. So you get this emotional blunting and increased resilience. That is not the way in which we think psilocybin might be working. So psilocybin works at the 2A receptor. So very specific. There are over 17 different types of serotonin receptor. This isn't going to blanket all of them. It's a very selective 5-HT2A receptor agonist. 5-HT2A receptors are mainly in cortex. This, when we look at imaging studies, it seems that when you give psilocybin or other psychedelics that work in the same way, you just get this like cortical disinhibition, which they've termed cortical entropy. Suddenly your cortical areas are all talking to each other in a way that they don't normally. This could decrease rigid thinking, leading to increased sort of sensitivity or flexibility. And this is thought to increase your well-being. Yeah, there's some data to show this. Let's skip through that. It works. Basically, latest results from imaging studies suggest that the rate of improvement of psilocybin is associated with this decrease in the modularity index, basically. So this is the Beck depression inventory. These are just showing those who responded to psilocybin, those who responded to citalopram. In the citalopram arm, even the ones who got better, that didn't correlate with this sort of change in cortical entropy or, you know, connectivity. Those who were treated with psilocybin, it did. Cool. How does all this relate to the rats? Well, 2017, we were much surprised to see some kind of unusual effects with a 5-HT2C antagonist. So for those of you who don't love talking about serotonin, which I assume is most of the people in this room, serotonin 2A and 2C receptors are functionally opposing. So an agonist at a 2A receptor should look functionally like an antagonist at a 2C receptor. Traditionally, I say traditionally, I don't know why, there's no like great tradition in serotonin research, but we haven't had a good 2A agonist that we can use. And all the 2A agonists that we can use basically just make the animals hallucinate. So if you give them something like Doi, they just sit there. Or they do these wet dog shakes. And so even though I did my PhD in impulsivity, that's my passion, that's what I was interested in, and 2A and 2C drugs work to modulate impulsivity, we'd never touch a 2A agonist because the animals wouldn't do the task. So we're like, meh, let's just ignore those. Instead, we worked with agonists at the 2C receptor and antagonists at the 2A receptor. And 5-HT2A antagonists and 5-HT2C antagonists have the opposite effect on motor impulsivity. So this is data from a paper in 2017. I could have shown you papers from 2001 showing exactly the same thing. M100 decreases premature responding. This is premature responding. Sorry, I should label that. SB242 increases premature responding. See, they're like yin and yang, opposite to each other. A 2C agonist does the same thing as a 2A antagonist. So that means a 2A agonist should do the same thing as a 2C antagonist, right? So a 2A agonist might be expected to increase motor impulsivity. What we were not expecting when we did this experiment was to see that a 2C antagonist could improve decision-making on the cued version of the rat gambling task. 2C antagonists aren't supposed to improve anything. They're supposed to be a pro-addictive drug. They increase impulsivity and increase self-administration of nasty drugs. And we were hoping to show that the 2C agonist did the opposite, and that maybe it might be good therapeutic. We didn't see any of that. We saw a 2C antagonist dose-dependently improving decision-making on the cued RGT. And Wendy analyzed it twice, make sure we got it the right way around. The only other task that I could think of or find evidence for that SB242 improves decision-making in is tests of reversal learning. it improves cognitive flexibility. It does so through the orbitofrontal cortex. So what Brett did as part of his PhD was figure out if local administration of the 2C antagonist does the same thing, intra-OFC. Yes, it does, particularly in the animals that are making riskier decisions, so the ones that are most vulnerable to the cue-driven effect. We see an improvement in score. So now we're going from more risky to less risky with increasing doses of the drug. Right? It's fairly convincing. 2 dose-dependent effects, I can't argue with that. One thing that we suspect about decision-making in the presence of these cues is that it is less flexible. It is more rigid. The reason we suspect that is because choice is less sensitive to reinforcement evaluation. So some of you might remember from your third-year level psychology classes that one of the definitions of a habit is that behavior doesn't change when the value of the goal changes. So you are no longer fully goal-directed if I change the value of your goal and you just carry on working, right? Here, if we change the value of the goal, which is the sugar pellets, by but allowing the animals to absolutely stuff themselves on those sugar pellets right before going into the gambling task, you'd expect they'd be less willing to work for them. And so in the uncued RGT, we see a decrease in choice of P2. Generally, animals sort of shift towards P1 a bit more. Decision-making doesn't change on the cued RGT. Even though emissions increase and latencies change and premature responses go down and all those things, the devaluation worked, it just didn't shift decision-making. We can make behavior sensitive to decision-making if we dump a 2C antagonist into the orbitofrontal cortex. Bottom line, we thought we had a really good argument for why all the behavioral tasks in the entire world, apart from maybe reversal learning, that psilocybin might affect, we really think it's going to affect behavior on the cued RGT. So we were very interested in looking at small doses, so microdoses, because we don't want the animals to be hallucinating. Okay? So these are very, very, very low doses of psilocybin. So a macro dose is probably about 1 mg per kg. The macro dose we said we might give in our animal care protocol was 0.3 mg per kg. This is 0.003 milligrams per kilogram. Data from 15 females, data from 15 males. The females show an improvement in score. So they become less risky, but we don't see it in the males. Why? No idea. Got the data last week. We don't know if it's because we're missing the dose that might be effective in males. We are going to try the high dose at the very end of testing. What we're doing right now, these 3 people here, we want to run the SPT42 drug in the same animals just to see if we can reproduce that effect, so we can do like a side-by-side comparison. We might look at ketamine in these rats too, and then right before we kill them, give them a big fat dose of psilocybin. Actually, we might run them the next day afterwards, right, to see if there's long-lasting effects, and then kill them. To see if we can use some CFOS imaging to figure out what's going on brain region-wise. I would suspect it's probably orbitofrontal cortex, but I could be. Implications, no idea. That's not supposed to be there. I stole these slides from someone else. So thank you very much for your attention. That is all I had to share with you. I know that this is quite a long one, but I hope that you might take the bit of the story that is, or the story that is most relevant to the research that you are doing clinically or pre-clinically. And I'm always, always, always happy to collaborate, to hear your thoughts, and to go on. So thank you very much. I don't have any questions. Let's see if I can bring up Zoom. How do I do that? Stop share. Oh, there's things in the chat.
I have a question, if possible.
Sure.
So I was just wondering, given the idea that the potential expected value of the sugar pellets that you give in P1 versus P4, basically risky versus less risky. Mm-hmm. What is the expected value of the timeout periods? If you were to look at a max, and yes. Then how much do you think that might be a part of your D2, D3 data in terms of that ratio of, how much pellets you could get versus the timeout, and like balancing those two ideas together?
Yes. So one of the things that Angela and Brett have done, Angela Langdon is a computational neuroscientist who is helping us model these data with reinforcement learning algorithms. And one of the first things she did was try and create a sort of a common, like, how do I explain this without sounding like an idiot? How many sugar pellets is like a second of timeout penalty worth, if you see what I mean? So they could be compared in common currency, because yeah, the increase in timeout penalties isn't linear. Even in the task, it goes 5, 10, 30, 40. And we don't know if the animals are treating 10 seconds as double 5. So, and in fact, the modeling data suggests they are not. So we've tried modeling it in a number of different ways, but one of the sort of starting points was to say, okay, so how many pellets is like 1 second or 0 seconds worth? Like, what's the actual cost in pellets of these timeout penalties? And first of all, that wasn't linear. So then we allowed them to vary independently. So there was like a like an independent, a factor that was independent for each choice, P1 through P4, that would basically determine how, you know, how many seconds did that punishment feel like to the rat, for want of a better word, in terms of how it altered the learning rate from those long punishments. And the bottom line is that when animals go risky, they go risky because they don't learn as much as they should from the punishing timeouts. So it's not because they hyper learn from the reward, at least not in the absence of a dopamine agonist. It's because they underlearn from the punishments. That's
so
not
I guess,
to say, yeah, go on.
To follow up on that then, like, do you think there's a possibility that the D2, D3 data could be driving this balance, one versus the other? Or do you think it's, you know, both of them, or one more than the other?
So to answer that question, we need to do the computational modeling, and Dr. Claire Hales is about to submit a grant to ICRG to do just that, basically to take all the data that we've got from both chemogenetic and pharmacological manipulations of the dopamine system and see if we can figure out which decision-making and reinforcement learning process that it's altering. If I was to bet, you know, it could absolutely go both ways, because the effect of the D2, D3 agonist is to basically wipe out the effect of the cues. I would expect that it would be both amplifying reward learning and inhibiting punishment learning. But then ropinirole, when Layli, we couldn't do the full reinforcement learning workup on her data, but she did look at win-stay lose shift analysis of the first 5 sessions, and she found that the effect of ropinirole to drive risky choice was significantly or entirely mediated by their persistent responding for big wins. So animals treated with ropinirole would get a large unlikely win and go back and repeat that action again, which is not what you should do if you want to succeed at the task.
I mean, yeah, I mean, awesome to your answer. I think that was really great. But you also sparked another thing in me, in terms of like, how much do you think then, if you're doing the modeling data, that the cues actually, do you think that it works as a reward in a way, like you know, just a natural reward in a way to the rodents or the humans? Do you think it's more of a rewarding process, I guess? And do you think you should take that into account?
Yeah, that's what we assumed. So we assumed that the cues were just going to be amplifying reward, and this was going to, you know, the grants and the papers would just write themselves. But it's not what we've seen in the majority of models that we've run so far, although we haven't modeled the dopamine data. So like I say, it's not impossible to drive risky choice by increasing response to big wins. But in the absence of the dopamine data, when we look at all the other cue variants that we've got, we see an inability to learn from the punishments being what's driving the risky choice. So if we mismatch the size or the interest value of the cue with the size of the reward, so now like the smallest reward comes with like the jazziest cue, we still get increases in risky choice, and it's still because the animals aren't learning from the punishments. If we cue the punishments only, then the animals learn really well. they become optimal decision makers, and they learn really well from the punishment signal. So it's not that the cues themselves are rewarding and they want to work for them. But when we when we cue both the wins and the losses, so like every time you choose P4, you're going to get a cue, whether it's a loss or a win, it's just going to go off like a, Christmas tree. Then we get the biggest increase in risky choice yet, and we start seeing enhanced learning from rewards as well as blunted learning from punishments. So
awesome. Thank you so much for that.
That's okay. I can talk about this for a long time.
Yeah.
Beck, you've got your hand up, I see.
Yeah, so you whizzed by that sort of different strains of cannabis negative urgency data. Could you put that back up? I kind of want to stare at it and scratch our heads and go,
Yeah, and I can also, hang on, there it is. For those of you who aren't sort of familiar with this debate, so originally there might have been a genetic difference between sativas and indicas writ large. Sorry, do we want like this one or do we want
the one that showed the
or
it was the negative urgency. That's the one. Yeah.
But so there's a cultivar of cannabis that is smaller and gives lower yield, and that is traditionally thought of as being the sativa. But even though anecdotally people who use cannabis will tell you that they will buy indica strains for very different purposes, like to relax, just chill out and get more of a body high, and sativas if they want to clean the house or like go dancing, scientists can find no reproducible, reliable genetic difference between things that are sold and labeled as indicas, or sativas, because it's just being done by growers who basically are just smelling the product and being like, smells a bit lemony, it's a sativa, or like, smells like gasoline, it's indica. But there is quite a bit of, there's a huge amount of heterogeneity in terms of the compounds that are also present beyond THC in different cultivars. So you can have cultivars with lots of different terpenes, different other cannabinoid products that I can't pronounce, have really weird names. And we'd have very little idea what any of these things do. And there's a hypothesis called the entourage effect, that all these other, or at least some of these other cannabinoid compounds are going to affect either the rate of absorption of THC or THC's effects, because some of them can actually have cognitive effects by themselves. Like limonene can alter performance on elevated plasmids, for example, and that's a terpene that smells lemony. So yeah, there's lots of, the thing that's really frustrating is that when you go and buy your whatever Bubba Kush thing from the cannabis store, you have absolutely no idea what is in it beyond the percentage by weight of THC, it's percentage by volume. And so the only 4 compounds that these companies are required to provide are THC, cannabidiol, and 2 metabolites of THC. Everything else they almost certainly would get from the NMR readout, but they are not obliged to tell us what it is. And yeah, so there's something between this particular sativa that is different from this particular indica, but whether it would generalize, we don't know. And we couldn't get this particular sample analyzed for reasons that are too torturous to go into. But now, from now on, we are going to analyze shit out of everything.
So I guess my question is, but what are the processes by which cannabis in general might influence negative urgency behaviors? And why would one strain be more likely to, like, what is it about? I know they can't find any differences between the different strains, but just hypothetically.
Well, they can't,
like, what interaction with endogenous cannabinoids or whatever that. you know, is going on in that complex swamp.
Well, when I say they can't find, genetically, if you just take everything that is labeled as an indica and everything that's labeled as sativa, you can't tell the difference. I.e., there could be an indica that's more similar to a sativa than it is to other indicas. That is not to say that if you took the most indica-y indica and the most sativa-y sativa, you would not find genetic differences between those two. So there are probably compounds like, you know, the things we just talked about, like terpenes and other cannabinoids that are going to be present in that extreme sativa that are not present in that extreme indica and are going to modulate theoretically the subjective and objective effects of those compounds, of that plant product, right? Because it's like 600 compounds altogether. So that could be why we're getting a difference between our indica and our sativa. But I can't tell you what it is that is driving that in these particular, like this compound that we bought from the government cannabis store. We couldn't get the products. We tried from the supplier, from Edison, and they would not give it.
So, because I'm just trying to wrap my mind around what's going on between like that whatever cannabinoids are at work, the dopaminergic system, the serotonergic system, whatever is sort of
it could be the cannabinoid system itself. Like, you know, it doesn't have to just be modulating dopamine and serotonin. I mean, cannabinoids, the system is complex and far-reaching in its effects. So from these data, we can't tell because this is all just systemic, but I suspect it's amygdala reactivity. So that would tie in with some of the things that Matt Hill has been looking at, for example, to, you know, one of the reasons that cannabis might be useful to people suffering from post-traumatic stress disorder is it could be sort of dampening the stress response in the amygdala. Right? So bear in mind the amygdala, Mel's about to do this experiment, we suspect is signaling like the negative consequences of choosing these options. If you were to change signaling in that region so that maybe either the negative options don't seem so bad, or there is a change in the way in which the amygdala is responding to them, or maybe it's a cortical thing that might then trigger you know, a go cheer yourself up, let's go response. I don't know.
Because arguably the amygdala could be responding as much to the gains as well, to the wins, right? Because we know it
could be.
This amygdala, you know, BLA is sensitive to reward too.
Yeah, in the absence of the cues, in the uncued version of the task, then BLA lesions will drive risky choice. But we don't know in the cued version, we haven't done. So that's why we think it might be amygdala. But also it could be accumbens, could be anything.
Well, this, you know, this data confirms stoner wisdom, which is nice.
Well, I think when we showed that THC increased or decreased willingness to work, Stephen Colbert took the piss out of us as doing the most ridiculous science ever. Like, yeah, well, we already know that. She's lazy. Anyway, any yes.
Really quick. Do you know if the oil you use is pure THC or did it also have like small amounts of CBD?
The oil was, yeah, definitely, it was the whole plant.
The whole plant, okay.
Yeah. Whereas the vape was pure THC. Yeah. So yeah, there's all kinds of other stuff.
Yeah, because one other thing I know about the sativa versus indica debate is like
Right.
Do you know if it was the sativa?
I'd have to look, like, zoom into the.
Yeah. Okay.
But it was, yeah, because they were supposed to be, both of them were supposed to be lower.
1% less than 0.05, and when we did the math back, it was like 0 across.
Yeah. Okay. Yeah, that's it. Thanks. Yeah.
Annie.
About your time of day.
So I should repeat the questions for the folks on Zoom. So someone asked what the cannabidiol concentration was in the cannabis oil, and Melanie responded it was very low, but it was a bit different for one of the strains than the other. And now Annie is going to ask about the time of day. Yes, so that is, I just need to convince a student to do it. So what I think we should do, if we're right, then this is quite important, to house some of our animals in a reverse light cycle room and some of our animals in the opposites. It's like standard cycle, because we do all our testing on reverse light cycle. And then test the animals at exactly the same time of day, but for one of them, the lights would have just gone off, and for the other, they've just gone on. Implant the ropinirole pumps, and then when we sack them, take half of it and either do half the brains and do either RNA-seq or metabolomics, and the other half and do CFOS. And see, I mean, because CFOS is, it's not inaccurate, but it's not like as cool. Yeah, absolutely. That's true. Yeah. So with court, I was originally thinking that this must be an arousal related thing. But if it is, then we'd be out of phase with the human data. Because for our animals, they're nocturnal, right? So their arousal peak is actually first thing in the night. So because they're on reverse light cycle, first thing in the morning. So when we're getting our ropinirole effect. Whereas for humans, it's the opposite, because they get the symptoms end of the day, when their arousal is going down. So it's possible, we should probably look at court. I mean, we're not court experts. Yeah. What I would like is a way of trying to figure out if this is in whatever analysis we do, if this is a melatonin driven effect. So to figure out if there is, either, I mean, we should surely see higher levels of melatonin in the animals that are housed in the dark, although brief exposures to light will tank melatonin. So as they leave the reverse light cycle room to be wheeled over into the operant chamber room, that light will shut off melatonin release. It has a half-life, I think, of about an hour, so we should still be able to pick it up. Certainly its effects on brain chemistry will still be present while they're being tested. But yeah, whatever secondary analysis you do, and I do not have the answers to what would be the best way of doing it, I would love that to be able to give us a strong indication whether we're looking at a dopamine melatonin interaction or something that's got nothing to do with melatonin or melanocortin. Yes, I think. I feel like I've read something where they did that. But yeah, you can tell that I'm just like super comfortable in this space. I was born to study circadian rhythms. Yeah, or you can definitely just give melatonin. So that would be the alternative, is to try and induce the behavioral effect by giving animals melatonin. But I think you can disrupt melatonin, but I think the mechanism by which it alters dopamine release seems super vague. Like, oh, it's going to affect calcium entrance through the terminals. Like, how does it do that? Like, that doesn't seem. Anyway, I have a lot of reading to do. Stan.
Before you see an increase in treatment response.
Right. We haven't looked at specific variation in. We haven't done it that way, but certainly if you sate animals, you see a decrease in. But with
Can you
question,
repeat the question?
Sorry, the question was.
Repeat the question.
Yeah, I'm going to repeat the question. Simmer down. The question.
Sorry.
The question was. Did I miss a question as well? No, I just said Annie's question. Okay. The question was, if the increase in impulsivity seen following cannabis administration, could that relate to the munchies, the hyperphagia that you get on cannabis? And I just said that if you sate animals, obviously you heard what I said, sorry. I was going to ask Melanie, do we see a change in reward collection latency that might indicate that they're faster collecting?
they're still motivated for sugar despite having like a mil of boost in a liter of sugar dietary fiber.
Yeah, maybe they're more motivated still, and that's what. might be
Yeah.
driving people.
It might be, like, I mean, yeah, it might be.
There's like old fight shows literature where it's a very
Right. Yeah. Yeah. I mean, if they were just really jazzed about getting the sugar pellets, I'd expect them to move faster, like either to choose faster or to collect reward faster. Generally, reward collection latencies are faster for the larger rewards, so we can pick up that, even from 1 to 4 sugar pellets, that sort of gradation. But we didn't see it. So if it is, it may not be the dominant thing driving it.
sex.
Always possible, because we did have a bit of a baseline shift. Yeah. And yeah. Oh yes, I asked them to do this. See, former me thought of that. Yeah, so it's probably not that. So the question was whether or not the poor performance, the lack of effect in males was due to the fact that they're slightly better at baseline. So their vehicle data, at vehicle, their males are better than females. So maybe if we looked at poor performing males, we could see effect of psilocybin. But when we co-varied their score performance, in the ANOVA, looking at the effect of drug, we still get a hugely significant effect. So it's not driven by baseline differences in score, basically. Even when you take that into account, you still get improvements in females only.
Could it be related to dose?
Like, we may just not have dosed high enough in the males.
Like maybe the baseline levels of dose would be different between males and females.
Yes, it might be. So that's, I don't know if maybe that's getting at your question. So maybe we just need a higher dose range. If we started at 0.03 and went sort of 0.03, 0.1, 0.3 in males, maybe we'll see it. But with the our current problem is that we are not allowed to hold very much psilocybin at all. And so that we've basically got enough to do one big dose for everyone. That's it.
Yeah, because it'd be interesting to know if like maybe there's just baseline dose differences between males and females rather than, obviously the score is different, but maybe you would see the same effect, but you just need a different dosing regimen, I guess.
And I haven't looked at the sort of receptor distribution literature in a long time for serotonin receptors, but a lot of it was based on, we'd cite papers from the 80s or 90s, and there's no way they did those in equal numbers of male and female animals. So I'm not sure in the rodents. Maybe it's coming out now because there is so much more interest in psilocybin, but we also don't have very many neuroanatomists left because people didn't think it was sexy enough to fund. So I don't know if we, as a field, know if there are sort of sexually dimorphic distribution patterns or densities of 5-HT2A receptors. The only people who might have done it are really only interested in prelimbic cortex. And that's Anastasio and Colleen. Yes, training questions.
Sure. Are you looking at differences?
We haven't, but we haven't in this study. We looked at 1, 3, and 10 mg per kg acutely in using a different behavioral task. And 10 mg per kg had the same effect as an IP dose of THC on that behavioral task. It was the cognitive effort task, but the rats hated it. So once they'd had 10 mg per kg, it was really hard to get them to drink it again, which, I mean, we don't have any like scientific measure of them hating it other than, the students reporting like it's really hard to get them to drink it. Yeah. So, and that also makes me concerned about drawing conclusions about what cannabis is or is not doing based on, delivery of a dose that is so high that the rats find it aversive and would never volitionally take it. So I wonder if that part of, at least at the top end of the dose range that we were giving IP in the first study we published on this, we were probably in that range. But 3 mg per kg they will take. And I remember you tried up to 6.
No, sorry.
Right. Yeah. Yeah. Tony. Mm-hmm. Right. So we're using 5 mg per kg and 2.5 mg per kg, but that's over a 24-hour period. So it's slow release. So it's going to be at any given instant when we. So the question was, sorry, trying to figure out how the dose of ropinirole that we're using in the mini pumps, how that relates to activation of autoreceptors versus postsynaptic receptors. When Tao Huan analyzed the plasma from the pilots, he was like, are you sure your pump was working? Because the dose is so low that you've got in circulating plasma. And I sort of said, well, yeah, but it's slow release. Like that's kind of the point. We've gone round and round trying to figure out if the dose we're giving is equivalent to the dose that human subjects might be getting. And it's really difficult to do the equivalency test because the rat metabolism is very different. So they're going to churn it up faster. And people don't routinely report blood levels of ropinirole for patients because it's not a clinically relevant test. Like it's not like lithium where it has to be within a particular range, like it works or it doesn't. Right. Maybe.
It's working by the autoreceptor, and you're shutting down the autoreceptor. Be a decrease in dopamine being activated in a sustained manner.
Right. Yeah.
We have a really good study of autoreceptor in vivo.